Back to our next lesson. So this lesson, we're going to be talking about total internal reflection. We'll talk about what that means, and then we'll be talking about the dispersion of light inside a prism, and we'll talk about why light disperses and creates a rainbow as well. And to do this, I have an applet here I'm going to use to demonstrate this. But before we start, hope that you guys tried these questions out. Let's go over the answers of this bell work here. Right? Just imagine a bell went off in your head beforehand. You pause the video if you haven't tried it already. If you have, let's see how well you did. Determine the angular refraction of a beam of yellow that enters zirconium that has an index of refraction of 1.92 from air at an angle 60. Okay. There's my zirconium coming at an angle from air at an angle 60 degrees. Okay, so 60 degrees from air. Air is 1.00. Zirconium is 1.92. We're trying to find the angle of refraction from less dense to a more dense, so it's going to bend towards. I'm assuming this angle is going to be less than 60 degrees. But don't know exactly. Let's figure that out. So let's call the bottom one 2. Let's call the top one 1. So sine theta 1, or 2, over sine theta 1. I'll put the 2 in the top, just because it's easy to rearrange. And then I have over here n1 over n2. So you put in your numbers. So we have sine theta 1, which is 60 degrees. And then on the other side, we have 1 over 1.92. And then we're just going to rearrange this to get theta 2 by itself, and then take the sine inverse. So sine 60 times 1 divided by 1.92 to the sine inverse. And I get, oh, that's a pretty big difference of 26.811 decimal degrees. But you notice that there's no decimal place on this angle, so let's just go 27 degrees for this one. Okay, a beam of red light. Okay, remember I was talking about red light would have a different index of refraction compared to yellow light. I don't know if I changed the number appropriately, but let's assume I did. Has a specific wavelength. Determine the wavelength, the frequency, and the speed of light in this. So this angle here doesn't really matter. They don't give me another angle, so I can't really use this angle because I'm not trying to find the angle of refraction. So let's just get rid of the angle for now. I want to determine the wavelength, the frequency, and the speed of light in glycerin. Okay, so let's start off with the frequency. And the reason I want to start with the frequency is because I can find the frequency right away, because the frequency is not going to change. So if I know the information beforehand, that information is going to be the same afterwards. The frequency is going to be speed divided by wavelength. So the speed of light, I'm assuming it's traveling from air, from air. So the speed of light of air is going to be, that was going to be a 3 at one point. 3 times 10 to the 8 meters per second. I'm going to divide this by the 650 nanometers. Now I've got to change the nanometers into regular meters. So you can look at your formula sheet for that. But that is 650 times 10 to the negative 9. That's what a nano is. Okay, so my frequency of light, red light here, is 6.41. I'm going to put that in 3 sig digs here. 4.62 times 10 to the 14 hertz. Okay, so I found my frequency. Now what I can do is I could just use this frequency to find all the other pieces, right? Well, actually, I know the speed as well. So let's find the speed. So if I can use the speed, I can use the speed and the frequency to find the wavelength. Let's find the speed. So one formula that I can use to find the speed would be this C over V formula. So speed is equal to C over N, which would be 3 times 10 to the 8 divided by the 1.47. Okay, so this is the speed of light inside the glycerin, which would be 2.04 times 10 to the 8 meters per second. And I could put these two together because this is the frequency, this is the speed. I can find its wavelength by going speed divided by frequency. Okay. So I typed all these numbers incorrectly into my calculator. You get 400. Actually, if you go through the math of it, it's 4.4158 times 10 to the negative 7 meters. But you notice that up here, this is in nanometers here, so I'm going to change this to nanometers. I'm going to divide by 10 to the negative 9, because that's what a nano is. You have 442 nanometers. There you go. Lots of different ways. You could use Snell's law there with the N2 over N1s. You could have done that as well to find out the new wavelength. If you did that, you divide the 650 by 1.47, and you get the same number. Works out pretty good. Yeah, this is just one way to do it. There's lots of different ways. Hopefully you figure that out. Okay. So the next part here, we're going to be talking about total internal reflection. Now to do that, I'm going to pull this over here. Okay. So here's my ray. I'm going to move my head out of the way here. Now, I'm going to turn on this laser here, and you notice that the laser just passes straight on through because right now I have water and water. The material here, say this is water versus water, 1.33, 1.33. So it's not going to bend if it just passes through a barrier from water to water. Kind of makes sense. It's not going to bend if the index between these two is also the same. Even if it was a totally different material, so maybe like one of those, I don't know if you've seen one of those balls that kind of disappear in water, they would just be like specifically designed glass that has the same index of refraction. So when you drop it inside the water, it just disappears. I'll show you about that. Okay, so in this video here, he has these two glass balls in his hand here. So when he drops them in the water, you notice that they just kind of disappear. It's because the index of refraction of those balls are the same as the water. You can see when he pulls that out, it kind of just appears. Right? You can buy these things in like Spencer's gifts and stuff. And they just happen to have the same index of refraction of the water, so they just don't bend light, so you just don't notice them there. Okay. Okay, so that's in this situation here. It's not bending. If I change the material, say the water, into something that has less index of refraction, like something like this, right? You can see that as change this material to be a less dense, something closer to air, it starts bending away. You can see there's a reflected angle here too. I'm not too concerned about the reflected one. Just worried about the refracted. You notice that reflected one doesn't change. Okay, so what I'm going to do here is I'm going to start off at a pretty steep angle. Okay, an angle straight up and down. It's very similar to this, but it's just going to be upside down. So I'm going up at 0. If I go up at 0, my reflective angle is also going to be 0. I'm going to go from water to air. So it's just an upside down picture here from water to air in this picture here. You can see, I see from water to air there. It's just going to be upside down. Okay, so 0, 0, you can do the math on that one. 0 to 0 just works out that way. Okay, as I move this over, say I moved it over 10 degrees, I can actually measure that out. And you're going to be doing this, well, I'll be doing this part of the lab here. I can move this 10 degrees and I can measure the angle on the outside there. We could do the math of it as well. So 10 degrees over, you notice that this angle here is like 12 point something, right? So it's changed. So it's bending away from the normal, which is what we expect. If I move it to 20, now it's at past 25, almost 30 degrees here. If I move it to 30 degrees over here, you can see now it's at past 40 degrees on this one. As I move it to 40 degrees, you can see now we're at 60 degrees. So the change is getting bigger on the other side. Just how the physics works on that. And then if I go to 40 degrees, Oh, that was 40 degrees. I'm at 60. If I go to 50 degrees, oh, what happened there? So you can see when I get to a certain angle here, just right about there, my refracted beam just disappears. You can see as I move this here, you can see that this beam here, the reflective beam, is kind of transparent. But as I move it down further and further, it gets more and more opaque because more and more is being reflected backwards. And if you look at the beam that's being refracted inwards, it gets more and more transparent. Just before it leaves, there's a transparency to it. It's not very transparent, but it is transparent. So around this angle here, like 50, 40 something, like 49, 48 degrees, just past that, it disappears. So nothing is going to be refracted into the material. It's all going to be bounced back. So this is what we call total internal reflection. It all reflects back from the surface. Nothing goes in, but all reflects back from that boundary that we have there. Anything afterwards is all going to be reflected. The angle in which it does this, the angle in which it reflects back completely, total internal reflection, measured from the normal line, is called the critical angle. All right? So from, say, water to air, the critical angle is around 48, 49. Okay? So what if I change this to a different material? Let's call that glass, something that has a higher index of refraction. Well, the critical angle is a much smaller number, about just past 40 here for that one. I can make this bigger, right? 60 degrees, or 1.6, sorry. Its critical angle is just before 40, so like 39 degrees or so. If I go to diamond, the critical angle is even going to be smaller, which means that there's going to be more angles on the other side of that critical angle where light will reflect back. So there's more chance the light will bend back and be reflected within the material. So that's why diamond sparkles so well, because its critical angle is so small. It means there's going to be such a large range of angles, I'll go this way, that the light will reflect back, and then it'll bounce within the diamond, and eventually it's going to escape, but we don't know which direction it'll escape, and it'll get that kind of sparkle to it. So how do we calculate this? That's the key to this one now, so I'm just going to remove this. We'll come back to it later. Okay. So eventually it's going to reach a point, like here in this picture. If we did the math, when you get to the 50, I want to mention that if I try to do the 51, what happens to the math when I try to do the 50? Okay, so I want to find this. Let's call this out here 1. Let's call this down here 2. I want to find theta 1. I want to find what theta 1 is. So I'm going to go sine theta 1. Let's move my head out of the way. I'm going to go divide by sine 50. Okay, that's 1, 2, and then 2 is on the top here. So I'll go 1.33. Oops, sorry. 1.33 on the top. And then the bottom will be N1. So this is N1 right here. So this is 1.00. Okay. So I'm just going to try to do the math here. So I'm going to go sine 50. Okay. I'm going to go times 1.33. And what I get when I do that is I get sine 1 is equal to 1.018 dot, 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 dot. Now I try to take the sine inverse, you're going to get an error. It says error domain on my calculator. Now the reason behind that is your sine ratio. What the sine ratio says, it says opposite over hypotenuse. To have a number greater than 1 here just means that the opposite would have to be larger than the bottom. Right? But what we know about the hypotenuse is always the larger side, so this number should always be less than 1 or equal to 1, right? But it can't be greater than 1. So this would give me an error. And when you get an error, you get that total internal reflection. Now, you notice that we had to do it this way, from light to air, from a more dense to less dense. If I tried to go the other way, I'll never get total internal reflection. So that's from air to water, okay? So keep on going, keep on going, keep on going. You notice that I always get refraction here unless I'm right on the surface here, which just skims across. But I'm always going to get refraction because it always bends towards. You want to get it so that when it bends away. So, put that back there. Let's go back here to glass here. So it's going to start bending away, bending away, bending away, bending away. Eventually, I'm going to get a critical angle here, where it's get a total internal reflection. There's no refraction down here. So the goal is to try to find out when does that happen. So if we look at the refracted angle here, it's getting closer and closer and closer until it gets to a certain value. So right here, it's the last time you see it. Or right about there, so it's the last time you see it. It's almost 90. So to find the critical angle, so measure from the normal line here, remember? The normal line here. So from 0 over here, that's 60 degrees. So it's 90. So to find the critical angle, we just say, what would the incident have to be to make sure that the refracted angle is 90? Because if it's 90, then it's bouncing back. You can see that's what's happening here. So it hits just about 90, hit 90, no more refraction. Now it's all bouncing back. So what does that have to be? So we're just going to do the math of that by just saying, well, here's a picture of what it looks like if you sit in the bottom of a pool. We're just going to say the critical angle to find it. We assume the refracted angle is 90 degrees. Okay, then we just do the math on that. Just find what the other angle is. So here's I want to do a quartz glass air interface. So we already kind of talked about this, but the only way we're going to get a critical angle on this is if I go from quartz to air and not the other way around, right? Because you always want it to bend outwards. So you could draw it this way. You can go quartz in the bottom. Its N value is 1.47. It's going to air, which is 1.33. We got a beam coming out. We know it's going to bend outwards here because it's going from a more dense to a less dense, or from a higher index of refraction to a lower index of refraction. I want to find out what the I is, the incident angle, to make this 90 degrees. That's the goal, to find the critical angle. We'll denote that here by calling this theta C. So it's the incident angle we're looking for here. So I'm going to go, let's move my head out of the way here. Sine, and we're going to label the two sides here. It doesn't matter which one you label which. Let's just call the bottom 2 like we usually do, and the top 1. So I'm looking for sine theta 2 when sine theta 1 is 90 degrees. Look at N2 on the bottom, 1.47. I'm going to put N1 on the top. Then we're looking for sine theta 2, which we'll call the critical angle. Okay, let's figure out what it is. So sine 90, if you know anything about trig, sine 90 is 1 divided by 1.47, and then take the sine inverse. So the critical angle here is 42 point. Well, I have no sig dig number, so let's just call it 42.9 degrees. There you go. Now, if I try to do it the other way, it just wouldn't work. You wouldn't be able to find the critical angle if I went from the 1 to the 1.47, because you'll try to take the sine inverse of a number greater than 1. It just won't work. So really only one way to do it. From a diamond to water interface. Okay, so from a diamond to water interface, what's the critical angle? So say we have water, which is 1.33. We have diamond. I think I put it on the bottom of this page, is 2.42. Okay, so to get the critical angle in this situation, we have to go from the diamond to the air, or to the water. We want it to bend away. So we're looking for this critical angle. We can call that the incident angle if you want to. Let's just put that incident angle for now, and then label this C. When this down here is 90 degrees. Okay? So I want to find, I'm going to actually list out the whole formula here. Oops, I started right in this way, so I'll just finish right in this way. Okay. You notice that these switched over compared to the other guys. Theta 2 over theta 1, theta or n1 over n2. Probably should have wrote it the other way unless I label the top 2 this time and the bottom 1. I don't know why I would do that, but I just did. And on the other side here, we have n1, which is 1.33. Oh, yes, that makes sense. 1.33, and then n2 is 1.42. In my mind, for some reason, I was thinking the number on the top is not 1. What's happening here? But it's being divided by something bigger. So this is going to work out 1.33 divided by 2.42 times the sine 90 up to the other side. So you're going to get like sine theta 2, which is our critical angle, is equal to 0.549 dot, 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 dot. So to find the angle, you take the sine inverse of both sides. And you get a critical angle in this case of 33.3 degrees. Cool. Oh, they give both numbers down here at the bottom of the page. Now, if you want to do quickly, the critical angle of air to diamond would be 1 over 2.42. Take the sine inverse of that. That'd be 24 degrees. So only 24 degrees of a 90 piece. So you can think of this in situation here. For this situation, for the diamond to water, 33 degrees. On the other side here of the 90 minus 33 is 57 degrees. So 57 of the 90, which is 63% of the light, is going to be trapped within here. So if your angle, if your incident array is somewhere down here, so this is my light here. If my light is in here, in this angle range, all of that is going to bounce back. Right? So all this light from 33 degrees or more is all going to be trapped in here. So a lot more light is going to be trapped in here than, say, just a water air interface, because this diamond is such a high index of refraction. Now, we use this in fiber optics and stuff, right? Whenever they talk about internet connections and TELUS fiber, they're using these fiber optic cables to do that. It's kind of a lossless translation of data because it's easy to decode light on or off, and electrical signals through wires can be lost pretty easily through interference. Now, you just have to keep the light within the fiber optic cable. You just have to make sure that you're always going to be greater than this critical angle. So you want the barrier between the glass and the cladding there to have a pretty large difference between the two. All right, so you want, so this, say, we're not going to use diamond for this, but you want this to be a high index of refraction. Maybe some scientifically designed material that has a pretty high number. Right? I'm not going to use diamond because it's not bendable, but let's just say, for the sake of this argument, you found some number that's N3, but you want this cladding or whatever's in between here to have an N value of maybe 1.2 or something. You want this distance or the difference between those two numbers to be as large as possible to give me this greater index, critical angle, greater critical angle. Okay? Because to find that critical angle, you're just going to take N1 divided by N2. As long as this number is, the further that number is away from 1, the larger your critical angle is going to be. No, smaller, sorry, the smaller your critical angle is going to be. Okay, cool. All right, the next video we'll talk about the dispersion of light, and we'll talk about refraction of different wavelengths, and just some things you're going to have to memorize or remember for certain tests. That'll be the next video. I'll see you then. Bye.